rock is use the tactics. So here are some common use tactics on this link, and I will be using some and explaining them on the go. But if you want some more advanced ones, or even if you want to implement your own tactic, you can just use the official documentation, and hopefully you will manage or consult the rock experts. Okay, so I want to use tactics to define my identity function to sort of match what we usually do in the proof assistant. So if I say definition ID2, right, and I'll give it the same type, so A type, and then colon A, arrow A, and then I'll just write the dot, and I'll check it, okay, and now here on the right-hand side, so I know for people who have used proof assistant before, this is super slow, just hang on a minute. This is for the pure beginners. On the right-hand side, it sort of gives me some goal to prove, right? Here it says, give me something of A, arrow A, and above the line is my context, right? So I know that A is a type. So then I write proof, and then proof dot, and then I can start proving things. And the way to prove something of a function type is you have to give it a lambda, right? So I say intros x, and now I introduced a variable called x, and now I give it a term. And, well, there are actually several ways you can prove this, but, I can just use the variable rule, right? And the variable rule I showed you from Martin-Löf type theory, this says use the stuff in the context. And the way I say my goal, what I'm proving now, what I'm constructing now, is just the stuff from the context, is I just write assumption. So assumption, and then I check it, and then it says check, there are no more sub-goals, and I can conclude the proof with the word defined. Okay, so assumption is the tactic that gives you the variable rule. Yes?
So can I quickly ask, who's Philip in the terminal?
Philip Hasselwater is my co-PhD student from my PhD student times, who was kind enough to help me set up my Bash profile and left his prints there, and I like it so much I kept it for years. So this is a tribute and a still thank you, Philip, for helping me out when I was a mathematician not skilled in software. Okay. Any questions about rock? No? Question, okay.
So above intros X, if we step backwards, it's showing A arrow A there, and when we step to intros X, we get A. I have trouble interpreting what's happening there.
Yes. So this is yes. So this is a lambda introduction. Okay. So maybe I can. That would be also useful, right? I can just show you the slides from Martin-Löf type theory, right? I have them here somewhere. Yes, good. So the lambda introduction rule is somewhere. Specific rules, okay? The lambda introduction rule is, this is lambda introduction rule. And it says, okay, I'll construct a lambda, and then it will move x to the context, and now I have to write b of x here. Okay? So this is the explicit use of the introduction rule from lambda, is the intros tactic, thank you. And it does lambda x for you, right? In the system, it's like writing lambda x, and then it says, I added this stuff in the context, right? So now I'm in this line, give me b of x. Yes. Excellent question. More questions about the rock so far? No. Okay. So we have assumption, but that's not the only one that we could use here. So for example, if I have a definition, a projection, okay? Proj, that takes a type, and then it gives me A to A to A. So it's kind of a current projection, okay? And then I will use it, I will use the tactics to construct it, and then I do intros X and Y. And of course I have a typo in Ross. And now it says give me a type A, right? So suppose I want to make the first projection, and then I write assumption, okay? I don't know which one is it, X or Y. Here I have two options. I have X and Y of type A, and the assumption will just choose one, right? And I can say defined here, and then I can print proj, and it's actually chosen Y, right? It chose the second one. I don't know why, it just chose whichever, you could choose whatever. But if I want explicitly for this to be the first projection, I can write exact X, and then if I print proj now, it's a function that takes X and something and gives me X, okay? So now I define the, sort of the first projection in this current form. So I personally usually just write exact here, and here you could give exact term, right? So instead of intros X, Y, blah, 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 I could just write exact, and then fun X, fun Y, X, right? So I can also show you this. Here I can write exact, and then fun X, where are you? Fun Y, X, and it should be the same definition here. So you can use interest, you can use exact, but usually you would want to use the tactics. Okay, now let's see how weakening comes in, right? Weakening is when I'm just adding stuff to my context. And for example, I can use, again, the projection thing. Now I'm going to define it in a slightly different way. I'll call it proj1 because otherwise it will complain. The names have to be unique, right? So I cannot reuse the name projection proj. And the weakening, so I can again do intros X and Y. But then suppose I want to write exact, and I want to do the identity function, identity 2 at X, right? I agree it's stupid to write the identity 2. I could just write X, but let's say A. Yes. I have to specify the type as well. So I could do this, but you see here in the context I have A and X and Y, and the identity 2 lives in the empty context, right? So I could just use the identity function here, and Rock implicitly used weakening to put it in the context here, and then it could use stuff from the context, right? So all of these weakening derivations that you have to write on the whiteboard in a derivation, it just infers it for you, right? So weakening always allowed, and this is where you see it, right? Identity used to live in an empty context, now it was used in a non-empty context, and it was all fine. Okay, that's not the most interesting rule, but I just wanted to show you that, you can see it. You can see weakening in play. Okay. Now again, something maybe for the non-rock experts that is not really connected to type theory itself. Doing this identity here, I had to use the type, right? Usually we just want to have it kind of let Rock figure the type out by itself, and we don't want to write it. So what we could do, so we can say check what is ID2 at natural numbers, and it will say, okay, it's a function from natural numbers to natural numbers, so I can partially apply my function, and then I get a function. The other thing I could do is say, okay, I had to write the type here, so ID2 at 0 will just fail, right, which is the correct thing to do. But I could say, figure out the type yourself and apply it to 0, and because 0 is a natural number, Rock is able to figure out what this implicit argument is, and then it will say, oh, okay, it's just identity at 0, and then there it is. One more point maybe, because we know that identity at 0 will compute to 0. Where can we see the computation rules? We can ask for them explicitly, okay? So one example would be that I can just say eval compute in identity 2 of 0, and if all goes well, it says this whatever you said is equal to 0 and it's a natural number. So I can invoke my computation rules, my judgmental equalities that are installed in the system, and compute away whatever the computation rules can compute away. When I was saying about the implicit arguments, I can also define the identity function. Okay, so let's take the identity 2, and I'll copy the identity 2 here, and I'll say, okay, identity, I don't know, what is 3? I can actually use curly braces here, and this will say that this is defined as an implicit argument, right? So if I want to say now identity 3 at 0, okay, check. Yeah. Now it doesn't ask for the type because it knows I don't have to specify it. I can still specify it if I want by saying a colon equals nat, and then it gives me the correct type. But if I say something here that is not true, which could be nat to nat, then it complains, right? So if you're specifying it, it better be correct. So type checking apparently works to some extent in Rock. Okay. Right, I already mentioned the beta rule. The other way we can see computation rules is in the simplifying tactic. So when you say simple, so we will see that a little later, just for the ones who know, because I was already talking about the computation rules. The simple tactic is actually where you can see that in practice as well. Okay. Now another maybe quirky thing about Rock that is not directly a Martin-Löf type theory feature, but something that people do get confused about, and I promise you that some of the confusion will go away, is the difference between ending the proof with defined, like here, and ending the proof with QED. Okay, so what I could do is, so I can, okay, I'll write a definition. Plus 2 in a transparent way will be a function from natural numbers to natural numbers, and I will define it to be plus 2, right, whatever it is. So introduce x, and then exact x plus 2, and then I will say defined. And now this is, the function that takes an argument and adds to it, like number 2. Nothing magical about this. Now the magic happens when I copy this function and make it opaque. Okay? And instead of defined here, I will write QED. Okay? And at the first glance, if I step to the proof, nothing happened. Okay? No complaint. So what's the difference between these two? What is the difference if I say defined here and QED here? And a hint about this is in the name. So if I say plus 2 transparent and plus 2 opaque, this means that I can sort of look into this guy, but I cannot look into this guy. So suppose I now want to prove something very reasonable, which is that plus 2 So I want to say that if I have an x, no, even easier, I can just say that plus 2 transparent of 0 is equal to plus 2 opaque of 0. Okay? The function is defined the same. So this should probably be true, right? And then I want to say proof. And then I want to say, okay, just reflexivity, I guess. And then it complains. And it says, well, I'm able to unify these two guys because obviously, on the first glance, they're not the same. So reflexivity tactic is, for those of you who haven't seen ROC yet, is exact the REFL thing, right? And REFL is called EQ-REFL. So for me, this would be the same as saying exact EQ-REFL, and EQ-REFL is the REFL constructor, let's say. And again, the same problem appears, right? Because it's expected to have this type, and I cannot unify these two guys. Okay, so how do I see the difference, right? The difference is that if I have a transparent one, I can say unfold plus 2 transparent, and this will unfold the definition, okay? So what this does is, so remember when we said in Martin-Löf type theory, when you write a definition with colon equals, it adds a new symbol and a new computation rule, right? So definition is adding 2 rules. When I say unfold, I explicitly say use the computation rule for this new symbol I defined somewhere previously. So unfold is just, another use the computation rule. And here it unfolds it, right? So now I see that the left-hand side of equality in my goal is unfolded, and it's 0 plus 2, and then I can do the promised tactic simple, and it computes it way to 2. So again, the computation rule for plus, because plus is defined similarly to what we did on the whiteboard with induction on natural numbers. This will compute, and I have 2. But unsurprisingly, if I try to unfold the opaque one, it will say plus 2 opaque is opaque, which, is self-explanatory because I named it the way it is. What this means is if I end my definition, theorem, lemma, I could have a theorem or a lemma here instead of a definition. There's no real syntactical difference between these. It's just like a meta reason. What do you consider is a lemma? What do you consider is a theorem? What do you consider is a definition? But if I have a definition and I end it with QED, that's very non-intuitive. If I have a theorem as a mathematician, so mathematicians end their theorems with QED. And this QED here makes it opaque, meaning I want to know that this is true, whatever I am proving here, whatever type this is, but I never want to rely on the structure of the proof, right? I want to say it really will never matter in my proof script how this was proven. I don't want to reconstruct it, I don't want to induct on it, I don't want to look into it, and obviously, if it's a function that you want to compute with, you're not going to end it with QED, you're going to have to end it with defined, and then, you can compute with it, and then you can look into it. So just be careful, sometimes if an error message like this happens, maybe you defined it wrong. Maybe you ended it with QED. So, but the benefit is that if your proof development is such that you want to know, you will never ever rely on how this was proven. If you have a QED here, the system will ensure that for you, right? It will throw an error if you try to do something stupid. Okay, question?
Well, what's the advantage then of using QED?
Yes, my last sentence. If you want to make sure that in your proof development, you will never ever rely on the actual proof of some statement, the system will ensure that for you. And mathematicians who design the language for mathematical proofs-ish typically want to do that. Typically they don't look into the actual proof construction. They just want to know something is true, and I want to rely just on the statement being true and not how it was proven. like mathematics is how it works. Computer science doesn't work that way, right? We want to use the programs. But if you want to use the way something was proven, you can just end it with define. It's like a safeguard for mathematicians. This is how I think of it, right? It's a safeguard if you want to say it never relies, something, it's proof irrelevant, right? I want to say I will never ever rely on the proof itself. I will just rely on the fact that it's true. Okay, question was there first.
I have two quick questions. One was, so +2 opaque is just a black box that's going to give you n+2, and also it's a proof of nat arrow nat?
Yes.
Okay, and the second question was, if you remove the parentheses from exact, I understand that it doesn't work, but I'm confused as why it doesn't work. Like, what does it think we are doing?
Oh, I think it's just how the precedence is like the parser. Like exact is a tactic and it expects one argument, and if I write a space here, it will try to apply to this argument, and then it's confused because it's not a dot afterwards. So it's just parsing. It's a design choice of the language. Yeah. There was a question there.
Sorry to drill into this opaque thing more, but is the reason why mathematicians prefer definition to be opaque, is that for some kind of mathematical reason, or is it more about maintainability of proofs, or is it about what is the actual motivation why it would work?
I don't know how to answer this question better. I think it's just because this is how usually mathematicians think, and they want to make sure that their picture of what is going on is correct, and then Rock enables you to have this picture. But we will get more into that opaque and not opaque thing when we talk about the universes and the existential quantifiers, and that's where it gets tricky. So keep your mind there, and maybe it will become more clear a bit later. Question?
Just wondering if using QED instead of define has performance improvement, or it's
Not really. So thank you for asking this question. I have it somewhere here. Right. QED versus define. It's on the slide. So what does define and QED actually do? So it does three things. First is it type checks or verifies the constructed proof. And then it creates the proof object in the environment. So the definition, introduces a new symbol and the computation rule in the kernel. And then the third thing is that it checks for termination if it's applicable. So actually what I can do, okay, I will just add this with admitted. So this is how you leave a hole. I will say fail. So this will fail, and I will end it with admitted, and this means I never really proved this thing. So if somebody is claiming that they have a full proof and they haven't admitted in their Coq script, then they're lying to you. The second thing I wanted to show you is that it actually does check for termination. So I can say something like fixed point. So fixed point is kind of like a definition, but it's making sure that it's a recursive definition. Okay, so this is explaining it will be a recursive definition. For some reason you have to do this explicitly. So I will do a stupid loop. Okay, I will give myself a natural number, and then I will end up in a natural number, and I'm using this on the I'm not using arrow. I'm using this syntax for a reason that I'll explain a bit later. Okay, so then I say proof, and I will give you exact something that will for sure not terminate loop of the successor of n, right? So you believe me that this doesn't terminate, right? I'm just adding on a successor every time I enter the loop. So, and I'm using it recursively. So far everything is okay, right? I could just write exact something that obviously doesn't terminate, and it's green color, right? But if I want to say defined or QED, whichever, it will not allow me, right? It will say recursive definition of loop is ill-formed, blah blah blah. It basically says it's not terminating. So let's see if QED does the same. Yes, right? So both of them try to do all of these three things. So they type check it, create the proof object, and check for termination. The difference is how you can use this newly defined symbol in the following, right? Will you ever be able to unfold it, pattern match on it, whatever, or is it just going to be opaque and just, a proof object that exists, so to say? Okay, so I showed you, was there any other question? Yeah?
I was going to say that in software, like QED seems great so that if people depend on your work and then you want to jiggle with it and mess with it, they won't be you will be allowed to do that without destroying them.
Yes. That's a good point, yeah. Okay. The other thing, okay, so this will fail. And I will do admitted, and please never ever use loop in the future proofs because it's a hole. The other way, so sometimes you want to, like when you do proof development, you want to like postpone some result for later and just leave a hole for it. So usually, now I'm going to explain for non-rock users. Usually you would want to like prove something, and then you want to have a result, so you'll just say, okay, this is a lemma, I will state its type, I will write admitted, and I will prove it later, and then I will come back to a previous thing and just prove the lemma later. So this admitted is like a useful thing while you're doing proof development, but not when you're claiming that it's done. The other way to do that is to use the enough tactic, right? So, for example, if I want to say again a transparent one thing, and then I have an interest x, and then I will say it's enough to provide some proof that is a natural number, or and a natural number, and then I will say like this, right? So I say, okay, I need to have a natural number, so it's enough to prove 1. Now I can just use exact n here, and it's happy, right? I say, it's enough if I prove this, and then I can use this one in my proof development, but it's introduced another goal, right? And basically that goal says, now you better give me my natural number, right? So I will use nicer, step to the goal, give me exactly n, step to the next goal, and then I will say, okay, now give me that thing in its exact n plus 2. Sorry, x plus 2. And then I say define. So I'm just telling you a little bit about mechanics. This is not really how you use type theories. I'm just saying that, if I have an admitted here, or enough here, or something, it's like, if you were deriving something and you wanted to think about what an argument was before. So, as an example, where is it? This one. So, for example, when I had this induction on natural numbers, and then I had my something, and then I knew this one was raffle, 0, and then something, but I wanted to leave this for later in my proof development when I was writing down the term. This is how, I would, and then, after I was done with the rest of it, I would, then figure out, oh, the type family was something, something. And this is the enough here. So this is how rock sort of mimics what you try to do. Okay. Next thing I wanted to say was the judgmental equality, how it computes away. Yes, I wanted to do that. So I wanted to do the associativity of composition. So let's try that. I can write definition, comp, the composition, and it will take several types, and I will make it an implicit argument. A, B, C are types, and then the composition will say if I have a function from A to B, and then if I have a function from B to C, and this should be big B. Why did you mean? The proof assistant. Then I have a function from A to C. Okay? And then I will define it.
I think it's code equal, yeah.
Yes. Oops. I will define it to be intros fg x, and then it is exact g of f of x. But I can also skip these parentheses, but not this one. Ah. There we go. Define. So this is how I define the composition. And remember the very big derivation that I told you I don't want to do this because it's hard and I messed up like 3 times while I was trying to derive it. Well, you see, now I don't have to anymore. Rog did it for me, you know, it just said comp is defined and it's well formed because Rog did all of the type checking and I didn't have to do anything. I just provided the definition and magic happened. So in the kernel, what it's doing is actually deriving the whole tree that you saw me do it on the whiteboard. Saw me try to do it on the whiteboard. Okay, now I want to do the associativity to show you where also intervals come into play. So, definition, a sock. So what is associativity of right, maybe we can do something better. I will define an infix notation so that I don't have to write comp everywhere. I will just use the circle, right? I will do notation. I always have to cheat when that comes into play. So it's G, and then I will use a circle, F, and this is defined to be comp of G, F. And I need the parentheses here. And then at level, and I have to give it an infix level. This means how tightly this infix operator binds, and I will choose a number 75. I don't know why it's 75. Somebody said 75 one day, and it always worked well. And I will say it's right associative. So right associativity is the word that I'm looking for, and this works. Okay, so now I can write G circle F or G composed with F. So the associativity okay, I will need many types. A, B, C, D at least. Any more?